of sessions back, how it actually works in practice. So if I throw the switch on this, I'm going to drive current through it, there's going to be a torque, it's going to want to turn. The wires here have a little bit the effect of being that Hooke's law kind of retarding force that I mentioned on Tuesday. We talked about galvanometers. In principle, it means the torque might not be strong enough to turn the loop fully to get into its preferred orientation, but in practice, I think the torque is strong enough in this case. But if we wanted to calibrate this in a way that the deflection was somehow giving us a measurement of the current flow, we would use that Hooke's law restoring force, drive certain known currents through this, calibrate it, and then mark up our scale, which this arrow would move along for certain known current flows. Okay, so this is how our galvanometer would work. So just to show you again the sort of principle of the galvanometer, I'm going to close the circuit. This thing turns, and if I turn it in the other direction, it turns in the other direction. Okay, so now you understand how the galvanometer design works, and you understand the underlying principle. Okay, so for the rest of the morning, we're going to turn our attention to calculating magnetic fields from initially moving charges, and then we'll immediately move on to talk about macroscopic current flows and see how that looks. So I'm going to do this in a sort of, again, compare, contrast with our electric field case. It's a little more involved, as you would expect. Magnetism is a more complex phenomenon than electricity. So, here we go. And I'm actually taking this more or less from our textbook because I like the way that they did this. So let me just first off remind you of when we were calculating electric fields, and we'll look at how this compares with magnetic fields. So, moving back a month, we learned that the magnitude of the electric field is proportional to the charge that gives rise to it. We also learned that the electric field goes as 1 over distance squared when we're trying to figure out the electric field some distance r away from our source charge. So that's basically all we needed to figure out our electric field for a point charge. It's true that the magnetic field is also proportional to the charge. It's true that the magnetic field also drops off as 1 over r squared. But we have two additional features of the magnetic field. Firstly, that it's proportional to the velocity of the charge. And then there's this curious angular dependence. How am I going to say this? The perpendicular behavior. Okay, I'm not quite sure how better to synthesize that, but those are the U phenomena that we have for magnetism compared to electricity. So, take a look at this sketch up on the right-hand side. It doesn't contain much information just yet, but you've got a positive charge in the center there, moving along the line in the direction of V, and we're going to try and figure out what the magnetic field at point B is, okay? And the r hat vector there is really just a unit vector pointing from where the charge happens to be to the point at which we're trying to figure out the B field. So, it turns out if I bring these things together, we can write this, and I know this is a little bit of a leap, but hopefully once you've looked at it a while, you'll see it's very familiar, that form. Okay, and maybe I would write this as a comparison, contribution to the electric field, 1 over 4 pi epsilon 0 q over r squared for comparison. Okay, so we have no difficulty with this, I would say. So what's similar? First off, there's some constant out front, which looks sort of familiar, but not quite. There's a q here, there's magnitude, in the sense I could have thrown that over there, got 1 over r squared. proportional to v, and the sine theta dependence, where theta is the angle between the velocity vector and the r vector. Okay? Now, that doesn't quite include everything we need, because it doesn't quite give us the directionality, and I'm going to just explore that a little bit more. It turns out, empirically, and we already know that there's this right-hand rule behavior, but it turns out empirically, the direction of the B field associated with this moving charge is perpendicular to the plane in which the R and V vectors sit. Okay? Let me say that again. It's perpendicular to the plane in which both the R and V vectors sit. Okay, fine. So let's say I'm at a point in that plane, this point P here. All that statement tells you is that the magnetic field is coming either out of the board or into the board. That's not quite enough for precisely uniquely specifying this. So we need the right-hand rule to give us some directionality here. So I'm going to write it in right-hand rule vector product form in just a moment, but let me first off tell you empirically or experimentally how the magnetic field looks. So I claim that here it's got to be either into or out of the plane of the board, and observationally it turns out that if I take my right-hand rule, but now really in this format, so it's a kind of slightly different right-hand rule, I'm taking my thumb now as the direction of positive charge motion, and I imagine just curling my right-hand fingers like this. So the right-hand fingers here illustrate the direction of the magnetic field at any point relative to the direction of the positive charge. Okay? What does this mean? Not the easiest thing to do here, but imagine I've got really big fingers and they wrap all the way around here. So up top, the magnetic field, as given by the fingers of my right-hand rule, is coming towards us. Okay? So up here, it's coming towards us. There's my usual representation for a vector coming towards us. If I'm down below here, but still in the plane, then the magnetic field is moving away from us, usual representation for that. And then you can imagine this as circular paths wrapping around this direction of positive current flow. So as I come around here, if I'm in a point that's kind of perpendicularly in front of the charge, my right-hand fingers are pointing downwards, and if I'm on the opposite side behind it, my right-hand fingers are pointing upwards. Okay? So let me just draw this in a slightly different way to try and make sure this is clear. Now I'm going to have my velocity vector coming towards me, so I'm looking from this vantage point, and the claim is, and this is what we observe experimentally, right-hand rule, the magnetic field lines wrapping around a positive charge that's coming towards us are counterclockwise circles. Okay? So this is what we observe. This is the right-hand rule behavior at work. How can we embed this observation with our kind of almost there representation of this? So what we're going to do is write it as follows. So, embeds the same information, but now we explicitly, unambiguously define the direction of the B field at any point relative to this moving charge. B cross R is a unit vector, so it has no magnitude, it's simply a direction. So in that sense, we're still left with just B here in terms of dimensions, the 1 over R squared here. So this now embeds that particular right-hand rule convention or observational of the direction that the B field is moving. Let's come back to this. We've got a constant up front, which is a slightly involved constant. The same way where we had with electrostatics, 1 over 4 pi epsilon. Let me remind you, this is the so-called permittivity of free space or vacuum. It's in a sense a measure of how easy or difficult it is to establish an electric field in vacuum. And then there's a 1 over 4 pi. Okay, now just to confuse things, it's very unfortunate that physicists didn't manage to come up with a smarter notation. We have a mu here, having just 10 minutes ago introduced a mu here. They are not the same thing. Okay, so mu zero here is what's called the permeability of free space. So it fulfills the same role. It's somehow quantifying how easy or difficult it is to establish a magnetic field in a vacuum. And again, I apologize for the fact that we inevitably end up with two different mu's in the same topic. Very potentially confusing. I'm not sure how best to have you distinguish between them. We're going to see mu zero a lot more than we're going to see this. But just try and be careful whenever you see mu from this point on to understand which mu it is that we're talking about. Okay.
So if it's not a vacuum, is it just normal mu?
Yes, even worse, right? Because, and we're not going to touch on this, sadly we don't have time, but there's a lot of rich, beautiful phenomena associated with it. You know, if I put a material in here, we go from epsilon 0 to epsilon. And it's true, if I put a material in here, we go from mu 0 to mu. Okay? So the permeability of the material rather than the permeability of free space. We are not going to do that, at least maybe I'll just be saying a few interesting qualitative statements about magnetism of materials. It's an incredibly rich, beautiful subject. But yes, Jess?
Okay, so there's mu and mu, which, okay, it's with an N.
Okay, so this is mu, okay? Mu, okay?
And then the other one's
We have news as well. This is mu, okay?
So no news here.
No news is good news, right? No, there is. But, just before the end of semester, there will be news. Okay? Yep, sorry. We're talking about electromagnetic waves. But for now, there's no news. Okay? All right. So, enough fun with animal noises. Okay.
Making an office again.
So, this is going to be our kind of working baseline for figuring out magnetic fields from single moving charges, or in just a moment, macroscopic moving currents. So, things to take away. The additional complexity associated with direction is easy to get confused, and no doubt all of you will. I do all the time. We're going to get confused with directions here, but otherwise you see where this comes from with a compare and contrast exercise. This is kind of interesting compared to this. As you know, we very often simplify our lives by putting a K here. If physicists had been sensible, they might have put KE here, and they might have simplified this by a KB. But we haven't, and part of the reason we haven't is because that's also false and constant. You see we're running out of things to use here. So you'll usually see it left in its full form in terms of mu0 and 4 pi. Okay? Here you'll often see K, but it's 1 over 4 pi epsilon. These two constants will turn out to be incredibly important at the end of the semester, because the relation between them turns out to have a very fundamental significance. But for now, let's just keep it as is. All right. Now, also on Tuesday, you'll remember when we had, and I apologize, I'm kind of going all over the place here, but you remember we had the force on a moving charge in an external magnetic field. It can be written like this. What we did on Tuesday was do a very simple analysis that allows us to go from a single charge with a certain velocity to a current moving along a length of current carrying conductor. And if you remember what I said at that time, is all we did going from here to here, this is distance over time, this is just charge. All we did is take the time in the denominator and combine it with this. So we ended up with charge over time, aka current. Okay? So the only change between this and this was moving time in the denominator here to time in the denominator here. Otherwise, it's the exact same expression, same physics. So it turns out we can do the same thing over here. We can take the time from this and put it in the current over here. So B equals mu 0 over 4I. We make this the magnitude of the current. This is now a length element times sine theta over R squared, or B equals mu 0 over 4I I L cross R, something like this, okay? So it's the exact same trick, just to get it in terms of a current rather than a charge. So we're going to make use primarily of the stuff at the bottom, because usually we're talking about magnetic fields produced by macroscopic currents. Let's see, there was something else I wanted to say about this. What was it? I have no idea. Yes, very much.
I have a question.
Okay. Remember when we started out with figuring out how to integrate over complicated three-dimensional, perhaps, but at least continuous charge distributions? We would often look at a small charge element, big Q, and figure out how it contributes to the total electric field, but with an infinitesimal contribution dE. So typically what we're going to do in this case is take a small current element, let me call it dI, or even more likely, just bear with me as I talk you through this because it's kind of important, is usually we'll have a setup where the current is constant and we're integrating over a certain length of conductor that's carrying the current. Okay? And so in that sense, the exact analogy to our starting point for doing integrations over macroscopic continuous charge distributions to find the electric field, the analogous thing to start integrating over to find the total magnetic field is something that looks like this. Okay? So a small contribution to the magnetic field from a small length element of current carrying wire where it's carrying a constant current. So we're not going to deal with situations where the current varies, we're just going to deal with situations where there's some particular geometry. We have to integrate with that shape. No.
So like these B fields are all like vectors, right? Because it's like cross product. Okay.
So here you see I've forgotten the vector nature. It just gives a magnitude. Here we've explicitly built in the directional information. What I would suggest doing in the problems we're about to work through for the remaining 25 minutes is forget about this format. It's already, worrying about the vector product here is already just a distraction, if you will. Usually in terms of doing the integration, we'll, as always, rely on some symmetries. We'll figure out if we have some canceling components, somatic components, and we'll integrate over this form that doesn't worry about direction, and then at the end we'll come back and say, okay, what do we know about the direction? Okay. All right, so let's take this as a starting point, and then we're going to work through a couple of standard geometries to figure out what the magnetic field associated with them is. You'll remember we had a handful of standard geometries for continuous charge distributions where I wanted you to know how to figure out the electric field. Analogous thing here, but it's in a sense even more limited in the sense that there are fewer standard geometries that we can easily analyze. And so I'm just going to do two or at most three, depending on how time permits. So I'm going to keep this here and do a first example, which is to figure out the strength of the magnetic field a certain distance away from a long, straight, current-carrying wire. I debated having you guys do one of these in class, but I'm not going to do that at the end. It's better to do it on the chalkboard. For those of you that are interested, I'm posting a pretty challenging calculation of B fields for a complicated geometry in my notes, but I'm not going to insist that you know that, because for those of you who like a challenge, you might want to look through that. So, long straight wire. Okay, so let's take a piece of long straight wire, like so. Let's say I have current going from left to right, and I'm going to try and figure out what the magnetic field at this point P is. It is a perpendicular distance, big R, away from the wire itself. And I'm going to take as a first starting point a small length element of the wire, the L, over here. And let's see, I'm going to draw the vector that points from this to the point of interest. So the analogous thing to little r up there. So that's little r. This direction. The velocity of or the direction, I should say, of the current is in this direction. So the angle between them is theta. Okay. A couple of you asked me after Tuesday's class, what does it mean to have a vector on a length here, and this is a scalar? Well, we know we define current as a scalar, but in fact the directionality of it is always important. So while it's a scalar by definition, direction is important. And so L in this case is the direction of positive current flow, okay, positive charge carrier. So there's dl, which indeed has a direction associated with it. There's r. And we're almost done. Okay, that wasn't a smart place to write I, but let's say that I'm going to choose L equals 0 at this point. So this particular element is a distance L away from my origin, defined here. All right. Now, as we have done in some of our electric field cases, remember we had an exactly analogous thing where maybe we were figuring out the electric field at a point distance r away from a long line of charge. So here we're figuring out the magnetic field at this point. Okay? All right, so first off, what's the contribution to the magnetic field at this point from this current carrying element? We're going to do the magnitude, and then we'll just briefly talk about the direction. So I'm going to take this. So dB, mu naught over 4 pi, and I have I dl sine theta over r squared. So I simply take that directly from here. And I'm going to do a trick here, which is not necessary, but just to show you the virtues of symmetries quite often. If this is infinitely long, and I think we did this at least in one example with an E field associated with an infinitely long charge distribution, I'm going to take this and I'm basically going to say, I'm going to split this in half, at L equals 0. I'm going to figure out the contribution to the B field from the half on this side, and by symmetry claim that it's equal to the contribution to the B field from this side. Okay? It must be true based on the geometry. The key thing to think about in terms of directionality is the magnetic field direction the same for every contributing current element? And the answer is yes, so this is where we're briefly going to talk about directionality. So I've always got my current going from left to right, that's the direction of my thumb. This is at a point which is in the plane here, but directly below it. So the magnetic field is always into the plane of the board at this point. Okay, so we need to get used to doing these sorts of quick calculations of the direction of the B field. And it's true whether I'm up here, it still contributes to the B field going into the plane of the board, or over here. Okay? So what I'm going to do is split this into two halves, calculate it for one half, and double the answer. Okay, it's exactly what we did for an infinite line of charge when we were calculating E fields. So I'm going to take 2 times the integral from L equals 0 to L equals infinity to get the total magnetic field magnitude. Okay? So, let's see, what else do I need to tell you about this? Sine theta, and again, a little bit of a twist here, but hopefully one that's pretty straightforward. What do you know about how sine theta, or theta I should say, varies? I'm doing this by looking at one half of this infinite line. If I've got theta on this side, which is an angle greater than 90 degrees, what's the technical word for that?
Obtuse.
Obtuse, thank you. So this is an obtuse angle everywhere over here. If I look at the mirror image side over here, it is an acute angle, right? But again, there's mirror symmetry here. But it turns out, as you know, that the sine of pi minus theta equals the sine of theta. So in this sense, because sine appears here explicitly, again, I need to make sure that the symmetry is correct and taking account of this, and it's fine in this case. All right, so what this looks like then is that it is 2 times the integral of that. So let me bring some of this out front. So this becomes 2 times mu0 over 4 pi. The current is constant. And then what am I left with inside the integral? I am left with sine theta dl over r squared. Okay, make sure you're okay with that. Just taking this and bringing the constants out front and leaving what I need to integrate over, what changes as I move along the line on the right-hand side. So here we're confronted with a similar problem we had with our electrostatics questions, which is we want to get this in form of a single variable that I'm going to integrate over. So there's a little bit of sleight of hand here needed to get this in terms of a relevant single variable. And our single variable in this case is going to be dl. So how am I going to figure this out? Well, again, this is exactly similar to what we did for E field and electrostatics. Remember that r squared is little l squared plus big R squared. So looking at this triangle, there's a right angle. Little r squared is big R squared plus L squared. So that gives me a way to cast little r in terms of L. And the other thing I can say is that sine theta, which also equals the sine of pi minus theta, is, let's see if I got this right, r over the square root of L squared plus R squared. Okay? So again, similar substitutions to what we did a month ago for E fields. So I need to take these two things, feed it back into here, and then I'm faced with my single variable integral, which I have to solve. And so it looks like mu0 I over 2 pi, integral from 0 to infinity of r over L squared plus R squared to the power 3 halves dl. Okay, I know we're moving relatively quickly here, but you've seen it before, Jess.
Where did you go?
2, 2, I've got now 2 here. 2 over 4. Sorry, 2, 4. I've got that. Alright, so this is the point where you've got a slightly nasty looking integral. As always, when you're confronted with something like this, I'm going to give you what the answer to the integral is. And it turns out it is mu0 I over 2 pi, that's still there. And then I have r here, and I end up with L over r squared, L squared plus r squared to the power 1/2. Putting in my limits. And it turns out, with a little bit of manipulation of this, that the answer is nicely simplified to that. Okay. So I'm just going to talk about the answer, and then I'll stop and ask some questions just to make sure you're okay with the whole procedure. So it turns out to only depend on the current and how far away I am. Okay? So let's see what this is telling us. So obviously the current, the bigger the magnetic field, it falls off as 1 over r. And again, the shape is given by my right-hand rule, wrapping around like this, wrapping around like this. So now we know that the magnitude and the direction of the magnetic field anywhere from a infinitely long current carrying wire. Nice simple result. Let me pause and ask some questions on the method. Again, exactly analogous to what we did for E fields or static charge distributions. Change a variable to get it in an easy format to integrate. There you go. No.
For comparison, what was the answer for the E field again? Just side by side.
It's certainly a 1 over r dependence. I don't know if that's as much as I remember.
Okay. Is it like lambda?
Yeah.
over
some units which I absolutely cannot remember, but you can easily figure it out by dimensional analysis, okay? As much as I can remember offhand. Probably have it in my notes. I don't like giving you incomplete answers in class. Does anyone know?